Pues, welcome everybody. Thank you for waiting. We have the pleasure today to have our second junior seminar. It was started by another student of Angel. And so another student of Angel, so, so you are the best. Please, the other ones start thinking of giving a seminar at some point. And he's going to talk about topological quantum field theories from representation varieties of links.
So thank you so much, Marina, for the invitation. Thank you for coming out. And today I'm going to present some recent results we have with Alejandro Calleja and Ángel González Prieto about TQFTs for representation varieties of links, yes, of torus links. So the outline of the presentation, I'm going to introduce the object we want to study, representation varieties, and I'm going to explain what kind of representation varieties we want to study about torus knots and links. Then I'm going to introduce the invariant, the algebra geometric invariant we want to study. There is the virtual class and the e-polynomial of these representation varieties. And I'm going to explain the three different approaches, and we are going to focus on the quantum method. That is the one Marina Olares, Vicente Muñoz, and Ángel González Prieto has developed, building a topological quantum field theory to obtain the virtual class of representation varieties. Finally, I'm going to explain some examples in different groups for representation varieties and new application of this method to nested torus links. Yes? So the first point is to define what a representation variety is. So we have a finally generated group, gamma, with a bunch of generators and relations, and we take a G-reductive group. We can think about GLN or SLN in the complex field. And the G-representation variety is just homomorphisms between this finally generated group and the reductive group. Yeah. So if we have an homomorphism, we can describe it with the generators and the relations. Yes. So this representation variety, thanks to the structure of the G-reductive group and the relations, it's an algebraic variety. So it's an object of algebraic geometry, and we can think that the group acts on it by conjugation. And why they are important? Because there is an important object. I'm not going to explain a lot of this, but there is an important object called G-character variety that has to do with the GIT quotient of the representation variety, the object we want to study, with the conjugation action of G. So in that way, we can study representations of the finally generated group up to base change. We can think about it as it. For example, if we take the finally generated group as a surface group that is given by this formula, the representation variety for a surface group is just describing how homomorphisms are in each generators and satisfying the relations we have. So we are going to focus on this type of representation varieties. We are going to consider the finally generated group as the fundamental group of a manifold. Yeah. In this example, we have surface groups, but we're going to focus on torus knots and links groups. And why they are important? If you have a Kähler manifold, we have the non-abelian Hodge correspondence. We are here on this vertex of the triangle, character varieties, and we have a correspondence between the moduli space of flat connections over the manifold. We are studying the fundamental group and the representation variety. And on the other side, we have the moduli space of Higgs bundles. So actually, studying representation and character varieties are very important to calculate some topological or algebra geometric invariants of this correspondence. Yeah. So now I'm going to present the manifold we're interested in, that are thanks to torus knots and torus links, not surface groups, but for knots. Yes. So what is a torus knot? Very simple definition. It's a knot that lies on the surface of an unknot torus with n times around the meridian, with n times in the meridian and m times along the longitude of the torus. And for the sake of simplicity, we're going to consider that n and m are coprimes. without loss of generality. Yes. And what is a link? A link is d copies of n torus knot displaced by a certain phase in the same surface, in the same torus. Yes. If we consider that they are not coprime, for example, the greatest common divisor is d. D would be the number of identical components that wins along the torus. Yes, this is the definition, but it's better understood with some pictures. For example, this is 5-7 torus knot. Yeah, you can see it from an upper point of view, and from the 3D point of view, it's winding along the torus. Yes, and what is a torus link? So we can consider the same knot and have a copy that is just displacing by a phase here. This is the 5-7 torus knot with 2 links. Yes, you have here some other views. This is the same from the upper, from the 3D perspective. So these are the geometry or the topological objects we're interested in, and we have to calculate, well, more examples here. This is the trefoil knot, and we can consider the trefoil knot with 5 links. That is this one. Okay, and we're interested on computing some algebra geometric invariants of the representation varieties associated to this torus links. Yes. So for that, we consider the knot complement. There is simply we can embed the torus and its knot in S3, and the complement is defined formally as S3 minus an open tubular neighborhood of the knot. So in this picture here, for example, the complement is just S3 minus literally this figure. Yes, tubular neighborhood. And we can compute the fundamental group of the knot complement, and of course it's knot invariant and a link invariant. Yes. So this is a key invariant, and we can compute it with the Wirtinger representation. So it's actually pretty simple to compute the fundamental group. And we're going to focus on torus knots and links that have a special presentation. That is this one. So if we consider S3, the 3 sphere, and the complement of the knot, we can describe the fundamental group of a knot as this presentation here. X to the power of n equal y to the power of m, when remember n is the number of winds we have along the meridian and m along the longitude. Yes, and for the torus link, we have this presentation here. It's a bit more complicated, but has to do with this picture here. We can consider here A and B as the loops of the meridian and the longitude, and F are the loops that takes one part of the link, then 2 parts of the links. In this case, there is the trefoil with 3 links. Yes, so we have a bunch of generator-bound relations, and we can study the representation variety for these finally generated groups. Some important things about these representation varieties. Well, we can describe for the torus knot just 2 elements of the group satisfying this relation here, and the same for the representation variety given by torus links. Yeah, it's just this expression here. Important things that we have to take into account when studying these objects. First, the representation variety is invariant on the isotopies of the link. So any variant that you can compute out this representation variety gives rise to a new invariant of the knot or of the link. And we don't have known abelian Hodge correspondence, as the manifold S3 minus the knot is not a color manifold. So it's a real 3 manifold. So we cannot use the triangle, the non-abelian Hodge correspondence to study this object. Yeah, so it's very interesting itself. Now, there are a lot of invariants we can compute out of these varieties, but we're going to focus on one that is very important in algebraic geometry, that is called virtual class. And from the virtual class, we can obtain the E polynomial. To define the virtual class, we have to define the Grothendieck ring of varieties, also known as the ring of baby motifs in algebraic geometry. Yes? So we take the Grothendieck ring of varieties over a field as the abelian group generated by isomorphism classes of algebraic varieties. This is a very simple idea. If we have 2 isomorphic varieties, then the virtual classes equal to each other. And then the relations of the scissor relation that enables us to define the addition operation in this ring is the following one. If we have a closed variety of x, then we can express x as the sum of z minus plus the complement. Yeah? This is a ring. We need to define a multiplication, and the multiplication will be given by the Cartesian product of two representation varieties. Yes? This ring has a very bad structure. Of course, we know that it's very difficult to understand all the structure of this ring. For example, the class of the affine line, A1 over the field K, it's zero divisor in this ring. Yes? And we will denote it by L, the class, and it's called left chest motif. So we can take a representation variety and calculate a virtual class expressing it as a polynomial in the variable L. Yes, so we can define the polynomial of the character variety. The virtual class is just the class of the object we want to study. If we have an algebraic variety X, its class in the Rothendieck ring is called the virtual class. And thanks to this, we can find a relation between virtual classes and the polynomials. The polynomial is this invariant here. It's a polynomial that is computed with the Hodge numbers of x. These coefficients are the compactly supported Hodge numbers of x, so we can recover the Hodge structure with this polynomial, with the virtual classes. And the E polynomial is the ring homomorphism from the Rothendieck ring to set the polynomials with variables u and v. In the context of representation varieties, we're going to consider the product of u and v equal to the Leschev motif. So all representation varieties can be studied just with a polynomial in a single variable. Yes? Okay. 3 different approaches to compute virtual classes. The first method was introduced by Hausel, Villegas, Letelier, Mere, Florentino, a lot of people working in this method, is called arithmetic because it's just counting the number of points of x over finite fields. So you have a set scheme, and you have a polynomial in one variable that satisfies the relation here, that the points over finite fields equals the polynomial evaluated in the number of elements of the finite field. Then the virtual class is given by that polynomial. Yes, this is the first method that we can find in the literature to compute the virtual class. The second, this was introduced by Logares, Muñoz, Newstead, Martinez, Baraglia, also working in this area, is to consider actually the representation variety or character variety and stratify it looking at purely the geometry of the variety. So you can stratify the variety into simpler pieces, and then thanks to the additivity of the virtual class, we can compute the virtual class of the object as the addition of the virtual class of every strata. Yes? And finally, we have the quantum method, that is the most recent one and the one I'm going to explore here in this talk. That is was developed by González Prieto, Logares, and Muñoz. And the idea behind this, it's like a combination of those two, but we will see that in the examples. But to use a topological quantum field theory to compute the virtual class in a recursive way. So we're going to understand what topological recursion means in this context. Yeah. So there exists a topological quantum field theory from the category of Born-isms to the category of modulus over the ring of algebraic varieties, the Rothendieck ring, so that we can compute the virtual class evaluating enclosed manifolds here in the category of Born-isms. Yeah. So now I'm going to explain how we can build this topological quantum field theory, and then our new results that apply this method to constructing an explicit topological quantum field theory that enables us to calculate the virtual class for representation varieties of torus knots, links, and finally nested torus links. So the first step is defining what a TQFT is. So a TQFT is a symmetric monoidal functor between the category of Born-isms with this monoidal structure, the disjoint union, and the category of vector spaces with the usual monoidal structure due to the dot product. So the topological recursion means that if we have a closed surface, we can decompose it into simpler pieces, and then we can compute in each piece the operator given by the topological quantum field theory in vector spaces. So as you can see here, this is a closed manifold. So we have a morphism as the symmetric monoidal functor respects the unit in every category. We have a morphism from the field to the field given by some topological invariant that we want to achieve. In this context, we're going to build one to compute the virtual class of representation varieties. And the idea is given by chopping this surface into smaller pieces and then combining them together. The advantage that has this method, for example, is that we only need to know, for example, for a compact G torus, a compact surface of genus G, if we can compute the operator given by the genus, we only have to do topological recursion to achieve the virtual class of representation varieties of G, of a G genus surface. Yes, this is going to be the idea that we're going to explore, but for torus links. Okay. We need a slightly different definition. That is a lax topological quantum field theory. That is only a lax monoidal functor. And instead of talking about vector spaces, we will work with modules. So we define the category of R modules with the usual monoidal structure with the tensor product. And it's exactly analog to that definition, but with a lax property. We will see that we need the topological quantum field theory to be lax in order to compute the virtual class. So the theorem due to González Prieto, Lolares, and Muñoz is that if we have a field, we fix a field, for any algebraic group G, and any n, being n the dimension of the board DSMs, there exists a lax topological quantum field theory that computes the virtual classes of G representation varieties for any category here of board DSMs in n dimensions, and being the ring, the Grothendieck ring of algebraic varieties. So the point is to consider a closed M manifold as a board DSM from the empty set to the empty set, and then this gives rise to operator that is just from the R from the ring to the ring that is given by the virtual class. Okay, so this is the main idea of the quantum method, to calculate, to compute these operators that allows us to not only calculate with the virtual class of one G representation variety, but to apply in some sense topological recursion to generalize results. Okay. So now I'm going to explain how we can build a topological quantum field theory. It's a composition of two functors. The first one is called the field theory, and the second one is called the quantization. Yes. So first, we are in the category of board DSMs. In this case, this is for general dimension, but in the drawing you can see better for dimension number 2. So we have here the handle element, the handle operator that contains the information of the genus, topologically speaking. So the field theory is the one that allows us to take one board DSM, its fundamental group, the representation variety, and also the maps that include the representation varieties of the boundaries. Okay, because we are in categorical language, we respect objects and morphisms. Objects here would be the boundaries as one. Morphism here will be the board DSM. There is the handle element, and then in the field theory we can span it's a span of algebraic varieties with two morphisms that are given by the restrictions of the fundamental group, the inclusion of the fundamental group, and then the restriction to the representation varieties of the boundaries and of the board DSM. Yeah. So if we apply the field theory, what we obtain is a span, is a correspondence with two morphisms of the representation variety of the upper one, the board DSM, and the representative varieties of the boundaries. Yes. The second one is the quantization, and it's I'm going to explain it in a few minutes, but you have to take like a Fourier-Mukai transform in this span that is given by the pull-push to obtain a morphism between the Grothendieck ring of varieties over this variety here and over this variety here, So we recover this idea of having the virtual class as a morphism between representation varieties of the boundaries. Yes? To be a little bit more precise, this is the field theory. It's a functor, symmetric monoidal, strong monoidal. When we break the monoidality of the functor, is in the quantization process. So we define the field theory as this functor on objects. We assign to any closed n-dimensional n-1 manifold X its representation variety. So on objects, you know that the span category has the same objects, and instead of morphisms, we have span between them. So we take the representation variety in objects, and on morphisms, it is on bordisms in the category. We assign to a bordism from x1 to x2 this span here, being p1 and p2, the restrictions in the representation varieties. The composition in the category of spans is just taking the pullback. If we have here another span, so we will take the pullback of this morphism and this morphism here, and this fiber product will be the composition of the span. Okay. The quantization process is once we have a span, we want to create this construction of Pulpus construction, Fourier-Mukai transform. Yeah. So for that, we need to introduce the relative ring of varieties relative to a certain variety, to a specific one. If we have variety S, an algebraic variety, we can think of algebraic varieties over this with a projection map, and we can define the relative ring of the category of varieties over S. So instead of calculating virtual classes, we can calculate relative virtual classes. They are not with a map onto the point, but with a map onto an algebraic variety S for any given S. And this construction is very important because it has some functorial properties that we take advantage of to construct the quantization. The first is that if we have a morphism between algebraic varieties, F, between X and Y, it induces a functor into the category of varieties over Y, a contravariant functor, and categories over X, thanks to the pullback. Yeah. So we have here an object in the category of varieties over Y. So we have Z over Y, and we have this map here of X. So we just take the pullback, and this object lives for this composition. With this composition in the category of varieties over X. In the same way, we can define another functor that is given by post-composition with the morphism. If we have a morphism G from X to Y, it now induces a covariant functor between the category of varieties over X and the category of varieties over Y, just being given by post-composition. Yeah. So we have here an element of this category, and then with simply post-composition, we have the element. This translated into the Grothendieck ring of varieties, if we consider the Grothendieck ring here and here, that it's perfectly defined. It's ring homomorphism, but this one is not. This one is a cover modular homomorphism. So this functor here will break the strong monoidal property of our topological quantum field theory. And this is necessary for computing the virtual class. Yes? So in this case, it's important to know that every algebraic variety has a map onto the point. So we can think about maps between the X and the point, and it gives the structure. I'm going to write it. If we have a variety S over a point, it defines a ring homomorphism given this structure of a cover module. Yes? So this is very important for computing the virtual class. So the quantization is the functor defined as. We take a span of varieties. Remember, the span of varieties encodes the information of representation varieties. And for objects here, for varieties, we assign the module, the cover module, K0 var over X, and on morphisms, that a morphism in Spanish correspondence here, we do this pull-push construction that is like a Fourier-Mukai transform. There is a morphism between the cover over x1 module to the cover over x2 module. Yes? This is a bit technical, but the idea is I have a span here, and I want to recover a morphism between modules associated to this variety to modules associated to this one. So I invert P because it's a contravariant functor, and then I can define this homomorphism. So the topological quantum field theory is just the composition of the field theory and the quantization. Given a Borodism, I can define a morphism over modules. Yes? So now we're going to study our new recent results. So in a way of how can we apply this idea to computing explicitly the virtual class of representation varieties of torus knot cell links, taking advantage of this topological recursion we're interested in. For example, we can see, as we have seen in the picture, that we can decompose a surface of genus G, taking the handle element. So all the topological information that we're interested in when talking about surface representation varieties is just given by this Borodism here. And this Borodism has an associated span, and of course, an associated operator between modules. So if we can understand the homomorphism given by this element here, we can apply topological recursion, and for only one, we can describe the representation variety for genus G. This is the same idea we want to replicate for torus knot cell links. So we need to find this piece of information. And this piece of information is given by the NM thickened torus. We are going to describe it. So first, we think of the knot and the complement, S3 minus the complement of the knot. And then we can think about decomposing S3 with the usual 2 copies of 2 tori, yeah? And what we want to describe is to encode the complement of the knot in a specific base. So if we have, we can cut the thickened torus transversely, what we would have is, this is why it's a thickened torus, the complement or the knot will lie over here. So if we want to compose with another one, the idea is to take another and composing here. And if we want to close this to obtain S3 minus the complement of the link, we take the inner solid torus, so we fill this with a solid tori. This is going to be the inner one, and then the outer one, that is the one of the decomposition of S3 minus the complement of that. So this is the idea. 3 important pieces for understanding this Borodism. First, the outer solid torus, this one here. Second, the one that recovers the topological information of the complement of the link, that is the NM thickened torus. Of course, it depends on N and on M. And the inner solid torus, that is the one we use to close here to obtain the closed manifold. Yes? It's a natural question if you're asking, okay, if you want to apply topological recursion, this idea here is not necessarily the same as a link, because the link has to be in the same torus, not inside a concentric torus. But there is an isotopy that we can find between nested links in this way with fixed N and M and the D copies of our torus knot. And the isotopy is given by the following image. So we take this knot here. You have to imagine that this is the complement of the knot, but for the sake of visualization, this is the same. And we have 2 pieces. This is thickened, okay? It's the NM thickened operator. And then we compose with the same knot inside it. So this is what we have. We have the same knot but inside the torus node, in the same way I've described here. So the isotopy is given by expanding the inner torus into the size of the second one. So just enlarging the second torus, we have this image here. So this is a torus link, and this is a general construction. So if we apply this topological recursion in d times, we have an NM torus link. This is the idea. So the operator is given by this expression in the category of vortices. Okay? And then we will see that we can enlarge the properties of this operator. But now we're focusing on torus links. So after the isotopy, we want to understand the fundamental group of our piece of information, the NM thickened torus. So the fundamental group is easily computed with the Seyfertbach-Campbell theorem and has this expression here. To understand this geometrically, AB, A1 and B1 and A2 and B2 represent the meridian and the longitudes of the inner and outer torus. This one and this one, yes. And as a direct corollary, we can describe the representation variety of this operator. That is just understanding how the four elements in G4 acts according to the relations of the fundamental group. So this is the analog of the piece of the handle element we have for surface, but for torus links. Now we have to compute the operators. We have to apply the topological quantum field theory in each piece. The inner torus, the outer torus, and the NM thickened torus, that is our operator we're interested in. So first, we compute the outer solid torus. So it's a three-dimensional Born-DSM that has boundaries, the empty set, and a torus. We denote with the bold T, the solid tori. Yeah. So this is a Born-DSM between the empty set and tori, and this gives inclusion of the fundamental groups. This is trivial, this is set, and this is set 2. And we apply our field theory to obtain this span of representation varieties that is given by this map here, that is the canonical one, and this one here that is given by, this is Q2, it's given by the identity and G, where we denote this, the representation variety of the torus. Just take two elements that commute in G, okay? So this is a big technical computation, but it's not very difficult to understand. If we take this operator here, the quantization factor, that is the pull push in this span of representation varieties, what we are doing is pulling here, a pullback here, and then a push here. So we obtain the morphism that is just taking the unit of this module of the Grothendieck of varieties. If we focus on single varieties, we have the usual definition of Grothendieck, and then we have by pullback the identity on the group, and then we need to push it to the representation variety of the torus that is given by Q2. So we obtain this relative virtual class over the Kavar module of over varieties over G2 because of this one. So we obtain G over G2 with the map that takes the element in G and send it to the identity and G. Of course, they compute. It's well defined. Now we want to understand the other operator that we will need to close the Born-DSM. That is the inner torus here, and it's kind of analog. Yeah. So in this case, we have the inclusion of borders. It's a Born-DSM from the torus to the empty set, and we can recover the fundamental groups, and we recover the span of representation varieties. And in this case, the map is just, instead of sending to IG, we send it to GI. So when we close, we recover the representation variety of an object. It's easily seen that you can compute the representation variety composing the outer tori with the inner torus, and of course, with the NM thickened torus. That is the central piece of information we want to study in our results. Yes? So it's a bordism between a torus and another torus, the inner and the outer surfaces. We have the inclusion of fundamental groups, and then we have the span of representation varieties. So as you can see here, we recover a cover over G2 modulo homomorphism thanks to this corpus construction. And the maps are really simple. We have, if you remember, that the representation variety has 4 elements with some relations that has to do with commuting in pairs, and then with some power maps that are the important ones when we are going to study it. But the maps here are just the projection over the first 2 variables and the projection over the second variables, the second pair of variables. These are the maps, P1 and P2. Okay. And finally, what we want to understand is, I have the outer torus here, so I have to compose it with the NM torus. And finally, we close. When I say close, it's like computing the absolute virtual class of every strata that we have defined previously. And what is the variety we want to stratify? The composition of the outer, that can be thought as the unit, with the NM thickened torus. Yes? And this is given by this pullback. So the image of this map, that is the one we had here for computing the outer solid torus. Under P1, the pullback of P1, that is the first leg of the span of the representation variety, is given by this pullback here. X will be the variety we're interested in stratifying. Yeah. So X is the fiber product over G2 of G, that is the part we recover for the inner for the outer torus, and the representation variety of our important bordism, the NM thickened torus. So this variety is explicitly described as this expression here. If we apply the morphism Q2 to find to end the composition of spans and quantizations, we got this morphism here. So X is the variety that you obtain when you take the unit in the first span of the outer torus and you compute the image of the operator given by the NM thickened torus with this map here, projection over the 2 last variables. And you can easily see that when composing with the inner torus, that is GE, we're going to kill this element here, and with the properties of the power maps and commuting elements of here, we recover the representation variety of maps, just composing with the inner torus. So this is what we want to study. We want to stratify X, not only for calculating the representation variety of a torus knot, but for finding how can we express this module, this operator here, and use linear algebra methods to apply topological recursion. So this is a morphism of modules, but if we can express this as a matrix form, we can just take powers of the matrix form and then compute the virtual class for any D-link for a certain NM for torus nodes. So in general, this module here is not finally generated. So we can understand it, but we cannot apply topological recursion unless we can express it in a matrix form, let's say. So we need to find a suitable submodule. So it's not only about stratifying X, the variety we have here. It's about proving that they are invariant under our operator. So we can express it in matrix form and then applying topological recursion. So the aim is to find a suitable stratification of X, not RG, but X, the composition with the unit. And after that, we can compose each stratum with this final bordism to calculate the absolute virtual class of every stratum. And finally, apply linear algebra methods to compute the G representation variety for an NM torus link. Okay. So to illustrate how we can do this idea, I'm going to explain some examples in the AGL1 group, the group of affine tensor arrangements of the complex line, and SL2. And finally, we are going to see how we can apply, we can take advantage of this method of topological recursion, not only to calculate varieties of torus links, but for a new object that has no literature regarding representation varieties, that is the nest torus link. First, we define the ideal one group as the group of affine transformations of the complex line. We're going to think of it as this matrix group with A being to C star and B to C. And then we take our variety X, we take G as this group, and we stratify this variety. So what we have found is we have three different strata that are auto vectors of our operator, and generates an invariant submodule where we can express these three strata of X in terms of generates an invariant submodule. Yeah. So the result that we have, this is the theorem we have here for the polynomial of the representation variety of torus link L and MD, is that we have three different strata that are eigenvectors. So in order to calculate and to compute the D component link, we just take powers of the matrix that we can explicitly compute here, and then we close with this form that is taking each piece of the variety and closing it with this fordism. So we compute the absolute virtual class here. So if we do this multiplication here, we obtain that the polynomial of the AGL1 representation variety of this torus link is given by this expression, taking the homomorphism from virtual classes to E polynomials. The second example is that we can do exactly the same for SL2. It's a bit more complicated. We have 5 different strata, but in reality we need 6 of them. And we can express the matrix in the following form here. It's a 6 times 6 matrix. So the operator in SL2 of the representation variety of torus links is given by this matrix expression. An application that we can find of this is that we can recover some previous results done by González Prieto and Muñoz. For example, talking about the representation variety of n-twist links. Yes? So in this theorem here, we have that the E polynomial of the SL2 representation variety of the twist-hop link that can be thought as a torus link with 1 wind in the meridian and n winds in the longitude is given by this expression here. So this is a torus knot, a torus link. We can apply our result, and this is the expression we find for the twisted hop link with n twisted. Yes, we have here our vector is slightly different. The matrix is not entirely diagonal. You have here one element, and these are the weights. When I say the weights are the virtual classes, the E polynomials of each strata. If you multiply this, you obtain this previously known result of the E polynomials. And to end the talk, I want to talk about nested torus links. So what is a nested torus link? If you have a torus link that is lying on the surface of a torus knot, we can do the same idea of the isotropy we used to compute the representation variety of torus links, and this just this idea. But what happens if we change the parameters of the NM thickened torus and the PQ thickened torus? We have this object is not a link because they have different parameters, NM and PQ. But it's a new object that is called a nested torus link. We can think of it as a cable knot also. So the idea is, can we find the fundamental group of these varieties? Yes, it's computed in one of the references of this talk, and it's far more complex than the representation variety of a torus link because it involves a bunch more generators and relations. But with this idea, if we can understand the operator given by the NM thickened torus and the PQ thickened torus, we can compose those bordisms to create a nested torus link. This is the formal definition of a nested torus link. You take different links with different parameters, NMD, not necessarily the same. For the isotropy, we need them to be D1 and MM to be the same to recover the link. But if we generalize that idea, it's a nested torus link, it's not a torus link. So we can apply our idea of composing bordisms with the different operators, N1, M1 until NR, MR, elevating them to this power. Okay? What is a nested torus link? It's better understood in an image. So this is a nested torus link. Okay? You have here the trifold 2 link out in the outer torus with 2 links. And then we have the 5-7 torus inside it. Yes? It's inside this link here. In this case, we have 2 links and 2 links, but this has not to be the same. You can put anybody you want. This is another side of these links here in the torus. And the same idea is applied, but we have a problem. For one of the invariant submodules, for one of the operators, we know that we can stratify and find invariant generators. So to obtain generators of an invariant submodule for one operator. But if we change N and M here and in here, the generators here don't expand the invariant submodule of this operator. So we can't literally apply topological recursion just taking powers of matrices. We have to stratify again the variety after we apply the second bordism. And to see the computations and to end this talk, I'm going to present some results we obtained to 2 links, 2 nested links for the group AGL1, and we can see that there are different interaction terms that has to do with the representation part. So to show the computations, we have here the first step, that is composing the first part of the topological quantum field theory. We have our stratification, usual stratification, 3 strata for AGL1. Then we apply our matrices, and we can elevate here the matrix if we want to take powers, to take the links. And then this matrix here is stratifying again every strata in terms of the new generators of the matrix form. So you can see that here there is no appearance of M1, M2, N1, and M2, because they lie all in the final step that is one of the most complicated when calculating it, that is calculating the absolute virtual class of every strata. So the idea in this example is I take 3 different strata, then I stratify each strata into the same idea, because we have a local trivial Taritsky vibration, and we can apply this trick in the algebraic variety. And then we multiply with the diagonal 9 times 9 matrix form. That is the same as putting 3 blocks of the operator. And finally, and what is most difficult, is to compute the weights of every piece. And then we recover the information of these nested torus links for AGL. So this is the end of the talk. And here are some references just in case you want to check. Thank you so much for listening. Questions?
I do have a question regarding that paper, actually.
Yeah.
Can you recover the results of that paper also in the SL2 case?
Yes. Well, the results here involve character varieties. We are talking about representation varieties. Right. Yeah, sorry, I didn't say that. The topological quantum theory construction is not about the G character variety, it's about the G representation variety. In some cases, it's easy to compute the character variety thanks to the representation variety, but in some not, so it depends.
I can say something about this. In this case, yes, because you are stratifying in terms of the stabilizers.
Yes.
Representation.
So you take options.
So you just need to, yeah. I mean, the question is, since you are
You can undo the
the
quotient.
stabilizer, you can do the quotient. It's just dividing between the virtual class of the group quotient by the stabilizer.
Okay.
Image of the structure.
And were you able to do a SL3 case, or I mean, that I get the answer.
Yes.
Finding those invariants and modules, and
In principle, you can compute the invariance module. And yes, we can do it. But it takes a lot of time and it's quite different because the generators are not so easy. But yes,
They are being honest. They can. Actually, they have an explicit description of the generators. The problem is that you want to compute the capping, and the capping is a mess. But
yes.
the generators are clear.
Okay. So we're working on, we have worked on giving an explicit decomposition of the varieties to be eigenvectors of the operator.
okay, that was my question. I know the final answer is a mess, but
Yes.
you know how to proceed.
We know an algorithm.
A way to proceed.
Yeah. Yes.
Okay, could you be able to apply the topological quantum field theory for different nodes inside a torus, like maybe not a torus link, or an arbitrary link who lives inside a torus?
We are thinking about it. For example, instead of taking this and I'm thinking of torus as the torus in a not torus, you can think of it as not torus. You take a torus and you imagine that it's a trefoil knot, and then you put there a torus knot. Or, for example, you can think about knots lying in two torus with two genus. So a figure 8 knot, I think that is not a torus knot, but it's a two torus knot. You can do it in a torus of genus number 2. So yes, you can use these methods to compute with the same idea, but the difficult part is computing the operators. Maybe the morphisms are very complicated, and then you can't stratify the variety. But in general, the idea is the same. The morphism is the same, but if it's twist, then the morphisms of algebraic varieties are going to be very difficult because of the inclusion of fundamental groups. So yes, it's an area we want to study, not only for torus knots in a knot torus, but also for different knots and also for different three manifolds. So you can take Sartre manifolds by a knot and then try to figure out what's happening there. But the maps are going to be terrible. So we don't know if we are going to be able to stratify that maps.
And do you hope that you are going to be able to obtain like a general topological quantum field theory for an arbitrary knot, or maybe that's too much?
I think that's too much. That's too much. But
Okay.
in principle, we can study some bit more complicated objects, like instead of one genus torus to two genus torus. But for any arbitrary knot, I think it's
Really too much.
Yeah, it's very difficult.
Okay.
I think the point is that you need to compute the operator for the torus. I think one of the morals of this work is that if you know everything about the whatever knot, then you can compute whatever about whatever link. That's the thing.
That would be the idea, yes. But for example, if you go to the operators of the here, these maps are very simple because of this as a knot torus. If you take a trefoil knot, you have to see the inclusions of the meridians and longitude parts of the outer torus in a trefoil torus. So these maps are going to be terrible. And then if you're able to stratify it, you could do it, but you have to study fundamental groups, inclusions, operators, and then algebraic geometry, taking Spartan, and that's it. That's it.
Very much.
Questions, discussions? No, let's thank wonderful talk again.
So, yeah.